Thanks for the introduction. Thanks for inviting me. It's a great honor to be giving a talk at the Institute. So today I'll be talking about explicit constructions for local properties of linear codes. This is joint work with Fernando Grana Geronimo at UIUC. So I'll define what error correcting codes are first. So they're simply speaking a subset of FQ to the N. And we want that the elements in a code are far away from one another for some formally defined notion of far. So there's many formally defined notions of far that people have studied in the literature, and we'll be looking at a few of them in this talk. But a good one to get started out with is minimum distance. So we say that a code C has minimum distance delta if for every pair of distinct code words in C, the elements of a code are known as code words. So for every distinct C1 and C2 in C, we have that their fractional Hamming distance is at least delta. Fractional Hamming distance is simply the Hamming distance divided by the length of the vectors n. One other important parameter attached to a code is its rate. It roughly measures the size of the code with respect to the space in which it lives in. So if my code C has q to the k code words in it, then I'll say that the rate of this code is k divided by n. So the closer the rate is to 1, it can only be at most 1. The closer the rate is to 1, intuitively, the lesser the distance will be between the code words because the space you're packing the code words in is finite. So if there's more of them, the distance between them will be less. So we can also have an encoding map for our code words, for our code. What does it look like? It is simply a map which takes in some vector in FQ to the K and it maps it to some code word in code word of C, which lives in FQ to the N. And in this talk, we are going to be talking about linear codes only. So linear codes are ones where the code C is a subspace of FQ to the N. And in this case, what will happen is that the encoding map is going to be a linear map. And the way to create the linear map is we will list out the k basis vectors for C, one below the other, in the form of a k by n matrix. And we left multiply a vector in FQ to the k to obtain a vector in FQ to the n, which is going to be the corresponding code word. And because there's k basis vectors, you see that all possible linear combinations of these k basis vectors will generate our whole code. Therefore, it's also known as the generator matrix of our code, of a linear code. So, and please stop me for questions if you have any at any point of time. So let's see how this is used in practice. So let's say Asterix wants to communicate with Obelix there on the right. And curiously enough, he wants to send a vector in FQ to the K, which is denoted as M. So what he'll do is he'll encode it using the encoding map. He'll get the corresponding code word C of M. This will be sent through the noisy channel. And Obelix will receive some vector Y at the end. And the question to ask now is, under what circumstances can Obelix recover C of M from Y? Okay. So let's look at this visually. Assume that these are all of our code words. And we have that the distance between every one of these code words is delta. So code has minimum distance delta. In this case, what I can do is I can draw these Hamming balls of radius delta by 2 around every code word. Hamming ball is simply a collection of vectors which are close to the center code word. So I can draw these Hamming balls of radius delta by 2. And now, if it was the case that Asterix sends C of M and Obelix receives the vector Y, then if it's the case that Y is only delta by 2 far from the sent code word, then there's only going to be one vector, one code word, which is delta by 2 far away from Y. And so Obelix can unambiguously recover the sent code word. Yes. So what happens if the number of errors is more now? If that number of errors is less than delta by 2, then we can handle it. But what if the channel is very noisy? In this case, what we'll ask for, we cannot get unambiguous decoding. There can be multiple code words which are close to the received vector. So we'll give up unique decoding, but we'll ask for the decoder to give us a small list of code words, maybe think 10 code words, which are close to the received vector. And if this, maybe it could be that we are okay with just having a list as well. But maybe we can also say that given the small list, we can prune the list and get the sent vector, sent code word as well. So let's see how this looks visually as well. So we have our code words here. And now we'll ask that for every vector in this space, if I draw a Hamming ball of some radius around it, then at most 3 code words should lie within that Hamming ball. So yeah, so I get that if I draw a Hamming ball here, I get this 2 code words in it, and then 3 here, 3, 2, so on and so forth. So for every where I place the Hamming ball, I want at most 3 code words to lie within it. It's a different notion of far now. So formally, this is known as list decoding, and the parameters are as follows. We say that a code C is rho comma L is decodable if for every y, vector y in fq to the n, we have that the number of code words agreeing at least 1 minus rho n coordinates with y is at most capital L. So think of capital L as 10 or something, and think of rho as a constant here. Okay. So this is generally well understood for the large alphabet regime. So what's the large alphabet regime? It is simply one where I'll fix a rho and a capital L, and then I'll say what's the best rate that a code can achieve for that rho and capital L. And I don't care about the alphabet size. The alphabet size can be as large as you want. Given that I want the code to be rho comma L is decodable with the best rate. That's what I mean by the large alphabet regime. In this case, the generalized singleton bound says that you get this kind of a trade-off when you want a code which is rho comma L is decodable with rate R. You cannot get radius better than this. So as capital L increases, this becomes closer to 1 minus R, which is the singleton bound. Okay. So for probabilistic results, we know that random Reed-Solomon codes achieve this generalized singleton bound. So this is saying you cannot go beyond this result. And now there are these results which say that this is tight. Okay, that there are codes which get this bound, and also RLCs were shown to get this bound as well. And more recently, there have been explicit constructions of folded Reed-Solomon codes. A family of codes have been shown to get these parameters for list decodability, and also codes over quantum size alphabets have been shown to get this parameters for list decodability. So let's look at the generalization of list decoding now, which is going to be relevant for us. So for list decoding, we were looking at the agreement of some vector y in fq to the n with a code word C. How did we map the agreement? We just looked at the coordinates where the entries are equal. We mapped them. That's what we did. But this was the case when the received thing at the end was a vector, where with certainty we knew that the first entry was blue, second entry was blue, and so on and so forth. But it could also be the case that the channel is so noisy that you don't know with certainty what symbol you receive at every coordinate. So it could be that the first coordinate you receive A with some probability, B with some probability, and so on and so forth. It's possible. So you can also then in that case you can talk about a received matrix. So then I'm saying that in the first coordinate I received these 3 elements with some non-zero probability, and second coordinate, so on and so forth. So the number of rows in this matrix is equal to the number of coordinates. And I can talk about now naturally an agreement with a code word with this matrix. So how would that look like? I would go to the first coordinate, I would go to the corresponding row in the matrix. I would ask if that element in the first coordinate appears in the first row. If yes, then I'll say that's an agreement. I'll do that for every coordinate. And so if I mark them out, I'll see that these are the coordinate / rows on which the agreement is happening.
So this matrix is really misleading, right? I mean, the columns have no meaning.
The columns don't have a meaning here, yes.
You just care about the set in every row.
Yes,
So
that is the this is easier to visualize. That's why I put it in the form of a matrix. But yes, I should mention that it's the rows of this matrix which are important. The columns don't carry any meaning. Yeah.
you have a set for the coordinate.
Set for every coordinate, yes. Set of small size for every coordinate. So I can ask then for every matrix or set of input lists, set of lists of size 3 for every coordinate, the number of code words that agree a lot with those lists is small. So formally, how does that look like? We say that for every matrix M in FQ to the n cross L, so L is the 3 in the previous slide, small l, we have that very few code words agree a lot with M. So formally, this is saying that now there's another parameter here, small l, which was not there before. Formally, we say that code C is row small l bigger list recoverable for every matrix M of that dimension. We have that the number of code words agreeing a lot of places with M is at most capital L. This is similar to the one for list-decoding.
So row is the fraction of coordinates where there's nothing?
Where there's nothing, they can disagree on row fraction, but if they're agreeing on 1 minus row fraction of coordinates, then that is a bad code word. Yeah. So it's agreeing a lot with M then. And it's a bad code word because, okay, it's a good code word in the sense that it's close to M, so it could be one of the good code words. That is the, you'll see why I'm calling it a bad code word in a few slides actually. But yes, that's the.
Because you don't want too many of them.
You don't want too many of them, yes, exactly.
Change perspective.
Yes, we'll change perspective in a few slides. Any other questions?
And what should I be thinking of the alphabet size as now, or
What should you be thinking of the?
alphabet size as now?
Alphabet size, think of it as some large constant, which depends on capital L, which depends on these three things. Yeah. Okay. So what are the applications for this? Why should we care about list recoverability? So it's a natural notion in the context of coding theory itself, as I presented in the last slide, but there's applications outside of coding theory as well. People have used it to build extractors in the area of pseudo-randomness, even expanders in that last citation for compressed sensing and also for heavy data algorithms. So it's a notion which has found widespread use in theoretical computer science. And now the natural question is, can we get explicit constructions of good list recoverable codes? Yes. So this is the question that is good to have in mind. So there's been a lot of previous work in this area. I'll highlight a few of them in this. I'll highlight a few of them in this table. So just to note, all these results are for the case where the radius is the maximum possible. So if you have a rate R code, then this is the maximum radius you can have. The epsilon is going to be a slack. It's going to be, you cannot get that radius exactly. You have to be a little bit shorter than that. Then we can talk about, once you have this radius, we can talk about what's the best output list size L you get once you fix the epsilon, which is the slack, the distance from radius, and the input list size L. So small l, I'll call as the input list size, which was the width of the matrix or the size of the lists for each coordinate. Yes, so the first major work was by Guruswamy and Rudra in 2006, where they showed for folded Reed-Solomon codes, which are an explicit family of algebraic codes, that you can get the output list size, which is a polynomial in the block length n. So the length of the code words is the block length. And you can get the output list size to be polynomial in the block length. And for the same family of codes, in fact, it was shown that you can get constant output list size, assuming small l and epsilon are constants. And we'll assume them to be constants for the most part. And the thing with these two codes was that they have good algebraic properties, but the block length, or rather the alphabet size, depends on the block length here. So it's a polynomial in n. And so in 2025, Srivastava and Tulsiani showed constant sized alphabet codes, which get constant output list size along with constant alphabet, and they're explicit as well. And there have been works in the probabilistic regime as well, where in a joint work with Rayleigh, we showed that you can get constant output list size with constant alphabet size as well, which is better than what was known for explicit constructions. This was later improved very recently, actually, by Brakensiek, Chen, Dhar, and Zhang, where they showed a smaller output list size. So smaller is harder.
What is this RLC?
Oh, I should have said that. That's a random linear code. So that is saying if you have a random linear code, so random linear code is what? It's one where the generator matrix for that code is one where you choose a matrix with entries uniformly at random, independently of one another. Yes. So for RLCs, you get this better in output list size. We showed that with constant alphabet size. Then this was improved more recently. And because of the techniques, they were able to transfer this output list size to explicit codes, specifically folded Reed-Solomon codes. And in our work, we were able to transfer this output list size to our explicit constructions as well. So this is our result where we show explicit list recoverable codes with constant alphabet size and ones that match this output list size, which was shown for RLCs. This comes very close to the lower bound. The lower bound only is missing a 1 over epsilon in the base. And in fact, I should also mention that if someone comes up tomorrow and shows a better bound for RLCs, then that automatically transfers to our result as well because of the nature of our result. Okay. So I'll talk more about the nature of our result now, but before that, I'll have to take a short detour to talk about an alternate view for both list decoding and list recovery, which will help us get our result.
You mentioned that you also get constant alphabet.
Oh, I didn't mention it. Sorry. Yes, it has constant alphabet size and the best known output list size bound for RLCs. Yes.
Sorry, you're saying, what is the comparison between the alphabet size for your work and this previous one?
So for this one and this one, yeah, the comparison is that the alphabet size here depends on the block length. So it's going to increase as you increase the block length. In fact, it's a polynomial in the block length, but our output, our alphabet size stays the same, no matter how large the block length is.
And do you have any opinion on whether you think this result for random linear codes is optimal already? Or
We think the answer is closer to this one. That is, this is the optimal one instead of this one. The difference is only that there's a 1 over epsilon in the base here.
And do you have any opinion on what the alphabet size should be?
The alphabet size, I don't know. So this is definitely not the best alphabet size possible. In fact, I feel even for this probabilistic result, that also is probably not the best alphabet size possible. It should look a lot cleaner than that, I feel.
Thank you.
Yeah. Any other questions?
So in none of these cases, the local lists can saturate the alphabet, right? Because the alphabet size itself grows with it.
In none of these cases, yes, that is the. It's always growing with the input list size.
You mean that's part of the definition of the question, right? Otherwise-
Right, but I could imagine constructing a codes where I want to tolerate, let's say, 1 over 10 fraction of all the alphabet symbols.
Mhm.
Such things will not be allowed in these constructions
Yeah.
because the alphabet size itself grows with little l.
I mean, 10% of little l grows with l, but
Yeah, but the dependence here is pretty.
Yeah, it's
Right,
not very good. It's exponential in L.
I see. So right now it's not even.
Right.
Is that your comment?
Yeah, yeah,
Potentially you could have allowed list recovery Up to 10% of the
Yes.
alphabet size, but
Yes.
right now we're way below that.
Yes.
We
Yes.
are like below the list.
Okay. Oh my God. Okay.
Still constant. But yes, it will be nice to clean up these alphabet size ones. And we were mostly, all of these works are mostly focusing on getting the output list size small. So that suffered as a result. You could think of it in that way. Yeah. Okay. So now I'll talk about an alternative view of list decoding and list recovery, which is going to help us get those results. It's going to be a generalization of list decoding and list recovery as well. So this is just to recap the definition of list decodability. And now the alternate definition that I'll present is going to be of the view where we are avoiding vector sets. We want to avoid vector sets of a certain format, so I'll list the properties of that here. The first one is saying that they have distinct elements. This is kind of redundant because I'm talking about vector sets, but I've had this for emphasis.
What's vector sets?
It's just a set of vectors. So think of,
The output list, for example.
yeah, these are going to be the output lists. Exactly. So I'll list the two other properties and then it will be clearer what the vector sets will be. Yes. So the second is that they will have to be of size L plus 1. This is the same as here. The third property is the most important one. It says that there is a center Y such that every vector in this set agrees with Y at a lot of locations. So these are going to be my bad vector sets. That's why I talked about them as a bad code word in the previous thing. So it's an alternate definition. It's equivalent to this thing. If you avoid all these vector sets, when I say avoid containing a vector set, I'm saying you should not contain all L plus 1 of them at once. You can contain L of them, L minus 1 of them. That's fine. Not all L plus 1 of them at once. If you do, then it's a witness for non-list decodability, because then this inequality is not satisfied. Moreover, I'm saying that as long as you avoid all these things, you will satisfy this inequality. Goes both ways. And this avoiding of vector sets view is going to be useful for us. Okay, and I should also mention that you can do a similar thing for list recovery as well. You can talk about avoiding vector sets for list recovery as well. Yeah. So we can generalize this more now. Now I'll just say that I'll talk about a code property which is just defined by exclusion of bad vector sets. So I'll specify my bad vector sets. I'll have some nice description for them, like in the previous slide for list decodability. And I'll say that my code, I want a code that avoids all of them, avoids containing all of them simultaneously. So what does it look like? Let's say that this is all of fq to the n. So this is not our code, it's all of fq to the n. I'll specify my bad vector sets. So we always take the vector sets to be of the same size. Here it's of size 3. Now I'll want a code that avoids all of them simultaneously. Can contain any 2 of them, can contain any 1 of them, but not all 3 simultaneously. Now the natural question to ask is, what is the maximum number of code words I can have in a code which avoids all of them simultaneously? What's the best rate of a code that avoids all these vector sets simultaneously? The more your rate is, the harder it is to avoid these vector sets.
And you still want it to be linear. You want it to substrate.
Yes. We want it to be a linear code as well for our specific focus. Yes. Okay. So let me move on to previous work on local properties that has been done. So this kind of viewpoint for codes originated with this work by Mosheiff, Resch, Ronzivi, and Saraf and Wouters. So this is Silas and Wouters. They showed a threshold type result for random linear codes. So what does this mean? It means that for every local property P, there is a threshold rate RP over there. So on the x-axis, I have the rate of a random linear code. The y-axis is the probability that a random linear code contains a vector set from associated with that local property P. Now, if you are even slightly below RP, the random linear code avoids This is the problem that it avoids the vector set. I'm sorry. So if you're slightly below threshold rate RP, you will avoid containing a vector set of P with probability close to 1. And as soon as you go even slightly beyond RP, you will contain a vector set for P with very high probability. That's what this is saying. This threshold phenomenon has been observed in a lot of other places as well, even for random graphs. So they showed this threshold type results for random linear codes. And this worked well in the small alphabet regime. So what's the small alphabet regime? Here, you do the opposite thing. You fix an alphabet size, no compromise, and then you ask what are the best parameters I can get for my local property. So it worked well for there. So for binary codes and all, it worked well, but it could not be extended to the large alphabet regime, this kind of local properties framework. Okay. The reason is a bit technical. I won't go into it. But then a few years later, in a joint work with Matan Levi and Jonathan Mosheiff, we introduced a notion of local coordinate-wise linear properties, which is, think of it as a subclass of local properties, which was designed to work in the large alphabet regime. And we showed a similar result as the one in the previous slide. We showed a threshold type result for LCs as well. And we also showed equivalence of random Reed-Solomon codes and random linear codes. So they get the same parameters, these two random code families with respect to LCL properties. This is what we showed in the work before. And let me motivate the notion of LCL properties with an example for minimum distance. So it might get a little bit technical, but let's see. So the bad vector sets for minimum distance is a local property. What are the bad vector sets for this? It's going to be all vector pairs that disagree at fewer locations than they're supposed to. What is this? It's same as saying,
You say pairs because you care about unique decoding now.
yes,
So L plus 1 is 2.
yes. L plus 1 is 2, exactly. L plus 1 is 2, so we are caring about avoiding vector sets of size 2 now. So we want to avoid vector sets which disagree at less than delta n locations. That's the same as saying they agree at more than 1 minus delta n locations. So now the idea is I'll move away from specifying vector pairs to specifying n by 2 matrices, same thing. And I'm going to specify these matrices in a way which might seem very contrived, but it will make sense when we talk about other properties. Let's specify the matrices by specifying an agreement, something called as agreement constraints on the rows. Actually, it should be constraints. Specifying agreement constraints on the rows. So what does one of them look like? I'll choose some 1 minus delta n rows of this matrix, mark them blue, and I'll say that the entries for each row should be equal. That's going to be my agreement constraint. Now, any matrix which satisfies these constraints, if I look at that, what's a matrix that satisfies these constraints? It's going to be those matrices where the rows marked blue, the entries are equal. So the entries are not equal between coordinates, they're equal in the same coordinate. And every such matrix which satisfies these constraints, it's a bad matrix. Equivalently, it's a bad vector set. Yes? But this is not enough. I need to have such a thing for every way I can choose 1 minus delta n locations from n coordinates. So I'll have n choose 1 minus delta n things. So I'll call each of them a local profile. I'll define it formally in the next slide. This is the setup for minimum distance. So now I'm going to have it for all such ways I can choose 1 minus delta n locations. Okay. And now I'm going to define LCL properties formally in the next slide, this slide, where I'm going to do a similar thing as before. Instead of talking about vector sets of size L, I'm going to talk about collection of star matrices of dimension n cross L. So this notation I just made up, just so that I'm saying the matrices in this, the columns in this matrix, they're all distinct. Because I want to talk about vector sets in the end, right? One other thing I'll say is that for list decoding, this will be L plus 1. This notation might be a bit confusing, so I'll clarify that. So I'll talk about collection of star matrices now. And I'm going to describe each star matrix. I'm going to describe collection of star matrices by using a collection of local profiles. So what's a local profile? I'll say that now, but before I'm saying that, I'll say that it's okay for me to define a collection of local profiles to talk about my property P. Okay, so what's a local profile? It's going to be a set of subspaces, one for each coordinate. Each subspace is going to be a subspace of FQ to the L now, capital L, the same L as here. Okay. And now, what is this local profile describing? It's describing collection of star matrices. Think of them as a collection of matrices for now. It's describing those matrices such that the first row lies in V1, second row lies in V2, third row lies in V3, and so on and so forth. Yes. So I'm using linear constraints on the rows. And that's the way I'm describing my bad matrices. That's the way I'm describing my bad star matrices. Think of them as that way.
The star just says that each column, the columns are distinct.
Distinct, yes, that's the only thing. It's nothing fancy, yes. And then to specify my bad vector sets, I can specify them by bad star matrices. And those bad star matrices are specified by specifying these local profiles. Okay. So let's maybe look at a picture. It's easier with the picture. So assume that this is the collection of all star matrices. So all these matrices have distinct columns. I specify my LCL property P by specifying one local profile. I look at the star matrices it's describing, specify my second local profile, look at its relevant collection of star matrices, and so on. Okay.
So
So
each profile is a constraint.
each local profile specifies a set of constraints, one for each coordinate.
Yeah.
Yes.
With constraints
Yes.
and so when you drew these
Yeah.
circles
Yeah.
here,
So the colors
What is that
maybe they
supposed
don't
to
match
mean
too
to
much.
us?
It's saying that so you have a local profile, and this can describe multiple star matrices. Right,
and
because
these are all the star matrices.
All the star matrices that's being described by this. So for each of these star matrix, the first row lies in V1 and second row lies in V2, so on and so forth.
I see. So you want to make sure, looking ahead, that for each local profile, the number of matrices satisfying it is no more than.
Yes, we want to upper bound that.
RGL.
Yes. That's the and this we are kind of also making the union bound more fine-grained in a way because we can focus on a fixed local profile and talk about that. We don't have to talk about it in a more general manner, which was done in previous ones. Yeah.
Why each VI is a linear subspace?
That is how we chose to define it.
And the distance equals equality, which is a real concept.
Yes.
Yeah, but like when you go to list recovery, why is it a linear subspace?
Yeah, that's a good question. So I'll show visually why list decoding you can talk about linear subspaces, and from that it will be clearer why for list recovery you can specify the bad matrices using linear constraints. It's going to still be agreements in the end. I'll show that visually in the coming slides, so it should be clearer there.
Okay, so another thing I'm confused is
Mhm.
so for each coordinate you have a VI,
Hmm.
and what are the like cross coordinate constraints?
Yes, so there's no cross coordinate constraints. That's a limitation of this framework.
But how do you ensure like one minus rho fraction are like equal or disequal?
Yeah, but that's only for between coordinates, right? So 1 minus rho fraction of the coordinates, they need to be equal in the same coordinate. That's the bad constraint.
In some rows, the subspace you allow is the full space. So there is no cross.
Yeah, I should mention
I see.
that also.
So basically you have V1 to Vn, and like 1 minus rho fraction of them will be identity.
Equality constraints.
Okay.
And the other things will be just, I don't care, anything goes. So that's a subspace also. All of FQ to the 2.
You can have a profile for every choice of row coordinates. So it will allow all kinds of
Yeah.
patterns that have row disagreement and 1 minus row.
You'll have many local profiles and choose 1 minus delta n of them for the case of minimum distance.
Yeah, but I don't see why you need other linear subspace other than identity, like equality.
That's the so for minimum distance and list decoding, yes, you only need agreement constraints, but there could be other local properties where linear constraints are more useful than just agreement constraints.
Okay.
And also, I should say that just talking about linear subspaces will help us to obtain our results also. It's a more generalized view of it, which
Okay.
is more helpful.
Are you actually adding constraints for disagreements, or you're just not adding
No.
constraints? Okay.
No constraints. So it's all of FQ to the capital L.
So the different color here will be different subspace.
So here I should mention that these are just matrices. These are fixed things. These are not subspaces. But here, this is a subspace. So if it's this hollow thing with dark blue color, that's one subspace. This light blue thing is another subspace of FQ to the L, and so on and so forth.
Okay.
So you can have, so this and this, they have the same color. So you can have same subspaces for some two coordinates also. That's okay. Yeah. Okay. Good. So that was the notion for LCL properties.
Oh, I guess the picture of a matrix is confusing because it says that all the columns are identical, right?
Yeah, it does. I thought about that, but this was the best way I could think of visualizing it. Yeah. So yes, so in this slide now I'm going to talk about how list decoding can be viewed as an LCL property. So if you want row comma 3 list decoding, what's a bad set of vectors to have? Well, it is one where you have some center vector y and you have 4 vectors which agree a lot with y. That's the bad thing. So now every one of these vectors is agreeing a lot with y. Let me map out that agreement here. So every column there has 1 minus row fraction of coordinates marked with the blue color, which specifies that first vector is agreeing with y with this vector at those locations. And I'll do that for the second column, third column, so on and so forth. So I'll call that an agreement pattern. And now let's look at this. If look at the first coordinate, if it's saying that the second and the fourth vector agree with y at the first coordinate, then that means they're also agreeing with themselves on the first coordinate. And so on, so for every coordinate. So I can just forget about the center vector y and I can talk about agreement constraints among the vectors themselves. And agreement constraints on the rows of this matrix. It's a linear constraint. So this is how you can specify why these vectors are bad for list decoding just by linear constraints on the rows, agreement constraints in this case. You can do a similar thing for list recovery as well. You'll talk about small L many subsets on each row, and you'll ask that everything in that one subset agrees with everything else.
So they are not just subspaces, they are coordinate subspaces. I mean, they all agree with them on the same basis. This is much more restricted. You need a general one, or you don't?
The general one, do we need it? It makes it easier for analysis just to have the general thing, actually. It's not harder. So
Yeah, I understand, but maybe your results can be stronger if you have
stronger. Maybe. That's also, yeah, that's a good question, actually.
Can you say again how the list recovery is expressed in this?
Yeah. So for list recovery, instead of this, you'll have a matrix of some small l. So you'll have small l you'll have n input lists. Each of them is of size small l. And then it's a bad thing if this entry here is one of these small l entries. And this entry can be one of these smaller entries. So if everything here if many things here can be described by these smaller entries, well, I'll mark which one of them appears in this set. And now let's say these two are the first element in that input list that they're agreeing with themselves, and then these two are the second thing in the input list, they're agreeing with themselves.
Okay.
So here is just one subset for every coordinate, but there it will be small L subsets. They all agree with one another. Yeah. Seems like a corner. Yeah.
So that will describe your linear subspace V1 to Vn.
Yes. Yes. And I'll have many such local profiles because there's going to be permutations of the coordinates. Yeah. Okay, good. So let's see. Right. So I described how minimum distance can be captured by this. I've described how list decoding can be captured by this, and also list recovery. I said it verbally. There's also many more properties that can be captured by it. So it's a very general class of local properties. Okay, it's not exactly local properties because it has to be described by linear constraints on the rows now, but it's still powerful enough. So now we're in a position to talk about the main result that we have. So what does it say? It says that we give a derandomization for all LCL properties at the same level of optimality as random linear codes. So few things that I have to talk about here, a few terms. Derandomization is just saying that you have a polynomial time algorithm, we give a polynomial time algorithm that constructs the encoding map of a code that avoids the vector sets associated with any local property P you want. So fix a local property P, we give a polynomial time algorithm for constructing the encoding map of a code that is good for that local property.
Polynomial in what? I mean, the
Yeah.
number of profiles is exponential.
Yes, yes. It's polynomial in the block length. Yes.
So how does it treat the input?
Sorry?
How does it treat the input?
The input is
The
just
exponential side.
going to be a message vector. It's just the linear generator matrix. It creates the generator matrix. It's a normal thing as before. So
Yeah, I'm not sure. So it's non-uniform in the property.
it's non-uniform in the property. So, okay, maybe I should say this before. We are assuming here that there's a uniform way to describe the vector sets of the property P for every block length.
So there is a succinct representation of your
Yes,
local
yes. The
property.
succinct
Not for every
representation.
local property, but for every.
Yes.
Very nice.
Yes, yes. It's for those things which can be described very nicely. That's there. The succinct representation, we talk about it in the paper. It's known as local profile description as well. So, yeah. So that's the derandomization part. And what do I mean when I say?
So let me just ask, how does it look like? Does it look like simply one profile, and then you say, I run over all possibilities where you can, this one minus delta locations where this happened, consider all of them.
So maybe I'll say it like this: like we don't specify the local profiles, we specify it as a fraction, like a list of fractions. So we'll say the first subspace in FQ to the L appears with this many fraction of coordinates, second fraction these many coordinates, and so on.
Yeah, and then
Yes.
so it's just the sizes.
Yes,
Yeah,
the relative sizes,
yeah.
and then we need to do some other operation on them, consists of applying a linear map. But at some point, you'll have to go through all the fractions which correspond to all the local profiles. That is there. But we are assuming that those are fractions which are rational fractions, so you can do them in constant amount of time. Yeah. So the level of optimality of random linear codes, what does it mean? It means that so in the previous work we had this threshold rate, which was the maximum rate at which random linear codes avoid vector sets of P. And we say that our explicit constructions get arbitrarily close to this threshold rate for P. And usually random linear codes get the best parameters for most of the properties that we have looked at. So it's most likely that these codes are also optimal for these properties, the explicit constructed codes. So before I go on with the main result, I'll talk about two important trade-offs. the first one, the important one is that there's an increase in alphabet size. So increase in alphabet size compared to the alphabet size that random linear codes get. This is the main reason we are not able to get binary codes on the GV bound or binary list decodable codes, which are big open problems.
The increase is exponential, if I remember.
Yes. So the epsilon, which was there in the previous slide, how close you want to be to RP, this is an exponential increase in 1 over epsilon. So there's actually the 2 raised to 1 over epsilon in the exponent now of the previous alphabet size, I should say. So that is there. And the second one is the linearity is going to be over a subfield. It's not going to be over the full field on which we define our explicit codes. Okay, but we still get the benefit of having generator matrices, parity check matrices for our code. So the first trade-off is the bigger one. See? Okay. So
what does it exactly mean?
So if you have if your field is over FQ, if your field is FQ, and if your codes are over FQ to the n, then if Q is a prime power, so maybe it is P raised to K, then they are linear only over P and not over the whole field. Think of it like that.
So this is the code after your derandomization.
Yes.
You'll show us the construction. right?
Yes, we'll show the construction and it will become apparent from the construction why it's linear over a subfield, actually, not over the whole field also. So what are the implications of this? The first implication is that if in the future someone needs a code property, and if it's an LCL property, then if they prove probabilistically that codes with some parameters exist, so if they prove a probabilistic result, then they can simply use a result as a black box and get an explicit construction for it. In fact, it has been used in this manner by Goel and Guruswamy, where they recently constructed codes with optimal proximity gaps by using this outline that I have mentioned in the first point. So that is one thing. And as I mentioned in the previous slides, we get the first explicit constructions of linear list-recoverable codes with that parameter. So 1 minus r minus epsilon radius, small l input list size, L over epsilon raised to R over epsilon output list size over constant sized alphabets. Okay. And as I mentioned before, that bound could be tightened if someone tightens the bound on RLCs, the output list size bound. Okay. We also show a small improvement in the alphabet size for optimal list decodable codes. So Geronimo, Mittal, Srivastava, and Tulsiani showed an alphabet size for list decodable codes of 2 raised to capital L raised to capital L. We get 2 raised to out of L. Small improvement. Any questions about this? Okay, I'll move on to the techniques then. So we use this local to global paradigm, which has been used a lot of explicit constructions previously. It mainly consists of 2 components. So the one is a small constant sized object, which because it's constant sized, you can find it by brute force and it will have the property that you want for your final explicit construction. Second one is going to be an infinite family of large objects that we know how to construct beforehand. And we use it to transfer the property from the local to the global level. Typically, it's going to be expanders. And it's been used in many code constructions, more recently for the C3 LTCs, quantum LDPC codes, and vertex expanders also. And another classical use, which we'll be using actually in our construction, is by Alon-Edmonds-Luby in 95. So they used it, they came up with this construction originally to construct codes with rate r, distance 1 minus r minus epsilon, and constant alphabet size. So distance 1 minus r is the best you can get if you have a rate r code. Singleton bound says that. And they approach that as closely as possible as they can with constant alphabet size. So rate Solomon codes get rate r, distance 1 minus r, but their alphabet size is it's a linear in the block length. So what I'm going to do is I'm going to present a primer on concatenated codes first. And then I'm going to talk about their proof for minimum distance in a reformulated version. And if I have time, I'm going to talk about our proof, which looks like a generalization of their proof now that we reformulated it. Okay, so let me talk about concatenated codes. Consists of two codes. One is the outer code, the other is the inner code. The outer code is over the large alphabet. It's an infinite family of codes. So the block length can be as large as possible. So what we'll do is we'll construct the outer code first. We'll have this encoding map which goes from FQ to the H. So the alphabets are from FQ to the H, and it's going to be a K length vector. We'll get an N length vector in the end. And now I'll reinterpret each of these large alphabets as a vector of small alphabets. So it's going to now be, each of them is going to be a vector with the entry sign FQ, and it's going to be of size H. I'm going to think of them as a message vector for my inner code now, and I'm going to construct the final concatenate code word using the encoding map for the small code, the inner code rather. So in the end, I'm going to get a vector of length FQ to the D times N. Okay, this is a common code construction. This has been used a lot of places. So how will this be used? So let's look at this reformulated proof for minimum distance. So this is from the AEL paper. It's a reformulation of their proof. The outer code that they use is one which has rate close to 1 and distance which is okay. It's epsilon cubed. This people know how to construct this. It's not very novel. The inner code is one which is formed by brute force. It is the code with the good property. So it has rate r, distance 1 minus r minus epsilon. And the way this is done is like this. We'll construct a bipartite expander graph, has n vertices on both sides, has degree d on both sides. And what we'll do is we'll take a concatenate code word, length d by n. The degree is d there, so I can place every inner code word for every left vertex. And I'll place every one of the symbols on every one of the d edges, and I'll push it to the right-hand side. It's going to scramble up this concatenate code word. And now I'm going to bundle it up at the right side. So every one of them is also a vector of length d at the right-hand side. And this is the alphabet size increase. This is the alphabet size increase for the AEL code, and it will also be the alphabet size increase for our code as well. So the final alphabet size is going to be Q to the D. Okay. This is the entire construction. You'll do the same thing for every concatenated code word, and you'll get the final code. So let's try to analyze this now. Okay. So how does
You
the
don't like need to iterate this or something? It's just
this is
things or-
this is the encoding map. So you take some message vector, which is going to be the message vector for final code. You will encode it using this concatenated code that you constructed, and then you'll do the scrambling thing. So two things. And the bipartite expander graph is constructible in polynomial time from previous results. That's the question. Any other questions about the construction itself? Okay, so let's look at the analysis. So, before I look at the analysis, I'll have to talk about how I look at the expander graph itself. So it's viewed as a sampler. What's a sampler? Sampler is simply saying if I color a 2/3 fraction of the right vertices, if I color the edges as well, then if I look at the left vertex set, a lot of the left vertices will see a 2/3 fraction of the edges also colored. So the way this is going to be used is it's going to be a proof by contradiction. We'll say that there's two code words which are bad on the right-hand side. We'll use the sampler to transport the badness to the left-hand side to many small inner code words, but the inner code words I chose were good. So that's going to be the proof by contradiction, roughly speaking. I'll say it in more detail in the next slide. So how does it go? I'll do this. So I skipped one step actually. I'll assume that the final code is bad in the sense that it's agreeing at all the places which are marked by red, and the ones marked by yellow, I just don't care. It's agreeing in more places than it should. The first thing I did was an unbundling
What's
step.
agreeing with what?
Yeah, I should be more clear. So this is agreeing with this is agreeing with this is agreeing with this, so on and so forth.
Sorry, can you say what you're proving now?
So I'm proving that the code that I constructed in the previous slide has good distance.
Just distance.
Good distance, yes. It's just minimum distance.
Okay, so here we have like two potential code words.
Words which agree a lot more
and they
than
agree
this
too
should.
much, more than they should.
More than this should.
Okay.
So then I do the unbundling step. I'm interpreting them as vectors only of small length. Now I do the construction in reverse now. I'll go back to the left-hand side.
But what do the colors signify?
Yes, so the colors mean that this is the same as this.
Okay.
This is the same as this, and so on and so forth. It's only between coordinates.
The light color is different.
Light color means don't care. It could be anything. Yes.
Okay.
So what is the inner and outer code used in this construction?
So the inner code. So now the inner code is going to be the code words of the inner code are going to be this.
Okay.
And before I had previously constructed the final code by taking some concatenate code word. The concatenate code word was constructed using the outer and inner code. And then I did this permutation of their symbols. Yeah.
Wait, so these are the inner codes. What about the outer code?
Yeah, we'll come back to that. So we'll come to that. I'll talk about the outer code now.
Oh, so this is like this bipartite graph is just the final step.
The final step was one where the things were there on the right-hand side.
Okay.
So you mean you first use the concatenated code to encode your input and then go through the bipartite graph?
Yes, exactly. Exactly. Any other questions? Okay, so for this, maybe I'll do this from the beginning. For contradiction, I'll assume that there's two final code words which agree a lot. So this agrees with this big thing, agrees with this thing, big thing agrees with this thing, and so on and so forth. For the yellow ones, it's don't care. If it's agreeing on these many things, then it's already bad for those right colored coordinates. It's the unbundling step. Pass to the left-hand side. And now I see that there's going to be a lot of, okay. There's going to be a lot of vertex on the lot of left vertices. The vector pairs are agreeing a lot. Particularly in this, they're agreeing a lot. It's not agreeing on all of them, but because I chose my inner code to be good, if it's agreeing on these many things, they'll have to be the same code word. That's what we get.
Meaning there's only one inner code word that agrees with both of them.
It's like this. If it's agreeing on more than r plus epsilon n locations, r plus epsilon d locations, but I had chosen my inner code to not agree on those many locations. So now if it's like this, then it could be any inner code word, but this is the same inner code word for both of these. And these things, they are agreeing at everything, so they are the same. And so zooming out a bit, I'll see that for many left vertices, the vector pairs agree a lot. This is from the sampler thing that I get. And now if I go to the inner code, if I look at the corresponding inner code words, I'll see that the pairs are all equal for these many left vertices. Now I'll go to the outer code. That will correspond to the alphabets for each of these left vertices being equal. Right? But then I had chosen my outer code to have distance, which is epsilon cubed n. So epsilon cubed n coordinates have not equal entries. And because the sizes of this set and that set, there should be at least one coordinate where the entries are not equal and equal at the same time. That's the contradiction. Yes.
When you analyze the inner codes, why there are permutations? I thought you block and
No.
code each one using the inner codes.
Using the inner code, I do. So the inner code, it's not, you don't transport the block as one thing to the right-hand side. You also permute the D entries within each inner code as well. They can go anywhere.
But it's within each block. It doesn't swap blocks.
It doesn't swap blocks, as in when it goes to the right-hand side?
Maybe I'm missing from the construction. So you start with your message and then you pass through the outer code, and then you flat the alphabet from the large prime power field to a vector field of the prime number.
No, you use an inner coder.
Oh, that is not a direct flattening.
No, it's not direct flattening.
Something that has distance locally.
But after that, you also have another encoding from like I think FQ to the H to FQ to the D.
That's the inner code.
That's the inner code.
Yeah, but the step between FQ to the H to FQ to the H, that's
the same. That's a flattening. That's a direct flattening. Yes.
Yeah, and the last step was like you have H coordinates as a block, and then you apply your inner code on that to get a D.
FQ to the D. Yes.
Yeah. So in your
Wait,
animation,
that's only the first. That's all what you described is just a concatenated code.
yeah,
Without the
this,
expander. And after that, you do this expander.
after this FQ to the D, have all the blocks, and then you do the presentation.
Yes.
Oh, there is another step that you didn't include in your slide.
Oh, it was there. So the thing on the left was a concatenated code, but I had already done that operations, the inner code, outer code, encoding operation. I already done that.
The flattening, you don't need to think about it. You can think of having, so many sigma different symbols, and you put them as vectors in FQ to the D in a way that's like with distance.
Okay, because I thought the depth for tree that you drew was the whole construction, but it is like after the leaf, you also have another expanded permutation.
Yes, exactly.
Okay.
Exactly. That's that.
The tree that he had, no, that was just describing the
Concatenated code. That was just a standard thing.
Yeah, okay. I thought that's your construction, but
No. That's one step.
Just to say, so the way you describe this, I mean, a lot of times people refer to this as distance amplification.
Yeah.
Right? You start with some distance.
Yeah.
And then it kind of gets amplified by this expander.
Yeah. Yes, you can. So you
enlarging that.
It's AL.
So you start with a code with this distance, epsilon cubed n, tiny, and then you get 1 minus r minus epsilon distance.
Right.
Yeah. Another way to look at it. So this is the reformulated proof for AEL. Up until now, nothing new has been said. But now, hopefully, I'll show the result which follows this. So we want to do something similar for list decoding. So contradiction. We want to do something for similar list decoding, specifically rho, 3 list decoding, let's say. So how will we follow the same template? The outer code is going to be same as before. Rate close to 1, okay, distance. Inner code, some rate r is going to be rho, 3 list decodable. It's a small inner code with a good property that we want in the end. Yeah. And let's say we do the same thing. We have a concatenated code formed by concatenating these two codes. We do the expand permutation shuffling thing. We get our final code. Let's try to analyze that. So for contradiction, we'll assume there's 4 code words which agree a lot with some center y. And now I mapped out the agreements here. So every vector, every column has a lot of agreements. As I said before, they agree with one another as well. That's same as before. Now I'll do the unbundling step, which I said, which just looks at them as vectors of length d now. This is so that I can transport it back. And this transporting happens in a very nice way because now I can say that for many left vertices, the vector sets will see the same agreement pattern as on the right-hand side, up to permutations, let's say. Yes, so I'm transporting the badness from the right-hand side to the left-hand side. Now I look at the inner code words now.
Why do you say the same agreement? What does that mean?
When I say same agreement pattern, I mean It's capturing, so
The amount of agreement is the same?
the amount is the same. Yeah, the fractional amount is the same.
Not the pattern.
Not the pattern exactly. Yes,
Okay.
yes. That's
So the
very
amount is the
important.
same just because of like sampler properties.
Yes, exactly.
Okay.
The sampler is doing a lot of heavy lifting here actually because there's multiple sets it needs to transport back fractionally to the left-hand side.
Right.
Yeah. So now if we look at the inner code, we'll see that there have to be at least two equal code words in every one of these vector sets. Why is that? It's because the inner code we chose to be row comma 3 list decodable. So it could not have agreed with that agreement pattern and had four distinct code words. So if it's agreeing a lot, some of them have to be the same. No choice. So I marked out the code words that are the same for these many vertices. But this was enough to get a contradiction before. Now it turns out it's not enough because when you go to the outer code, you'll see that there's two equal alphabets for every one of these coordinates. But it's not enough to get a contradiction because the outer code, the guarantee is very weak. The guarantee only says that for some epsilon cubed n coordinates, the first two, the alphabets will be not all equal. That is just following from the distance of the outer code. You choose any two columns, choose any two outer code words, you look at the entries, some epsilon cubed n coordinates will be not equal. But the problem is this, it's possible for a coordinate to be not all equal and still have at least two equal alphabets at the same time. This was not a problem when the vector sets were of size 2, because if the vector sets were of size 2, and if you had a coordinate which has greater than equal to two equal alphabets, you had all equal alphabets, and you cannot be all equal and not all equal at the same time. So when you go to size 3, even this kind of thing fails. You want to fix this? How do you fix this? More encoding? No. We don't get a contradiction, but what we'll do is we'll choose a stronger inner code actually. So let's look at what it was. Again, I've copied this from the previous slide. From the assumption of the bad final code words, we get this implication in the end. That was the outer code word guarantee. And if you went back in the chain of implications, you'll recall that this came about because the inner code guarantee said that for every bad agreement pattern, the vector set will see at least two equal code words. Now, if I change this to say that the vector set will see all equal code words, this will change to say that for these many coordinates, there'll be all equal alphabets. And then that will be contradicting that thing. So if I change this to all equal, I'm happy. Question is, can we do it? So our answer is yes, you can do it. The inner code guarantees that for every bad agreement pattern, you want every vector set to contain all equal code words. Put a star here. It's not technically correct, but for understanding, I'll just keep it like this. This is the new improved guarantee, and this is the crux of our main result. We prove that such good inner codes exist with this probably stronger requirement, probably stronger guarantee. It's an inner code, constant size, find it by brute force. You use it, you do the same construction as before, and you'll get what you want. The good thing is that the rate is the same as it was before. You don't lose in the rate, even though there's this probably stronger guarantee that it's getting.
Can you say formally what's the property?
You'll have to look at a agreement pattern on maybe some two code words. It says that there exists a sub-agreement pattern on a set of code words which is less than size 4, such that the random linear code, if it satisfies that sub-agreement pattern, then the code words have to be all equal. So this existence of a sub-agreement pattern, that is the technical thing that I am omitting here.
And this has the same rate as
Same rate.
your previous, it's called LCL.
Same rate as a normal list decodable code. So the one where I had the weaker guarantee. So
But I thought the inner code will be a random one
Am I
that
showing this?
achieves
Sorry?
some. No, I'm saying I thought the inner code will be some random code that achieves your like
This decodability.
what's the word, like LCL stuff?
No, less decodability.
Pattern.
The bad agreement pattern.
Yeah.
So it is this. So the inner code guarantee is that every vector set will contain at least two equal code words, because there was a bad agreement pattern here, which the inner code words were
So
satisfied.
here you're just instantiating your LCL to list decodability
Yes.
of row 3.
Yes, exactly.
And for this, you can prove what you said, like you can enhance the
stronger.
guarantee at the
Yes.
same rate.
And I can do it for every LCL property.
Oh, for every LCL property,
I can do that thing,
you have a
similar thing.
transformation to some other
Yes.
property,
Yes.
maintains the rate.
And gets a stronger guarantee for the inner code. Yes.
And the catch is you blow up the
Alphabet size. And the linearity is over a small field, because if you remember, we were bundling up the alphabets here. That's increasing the alphabet size, but the linearity is still over the old field.
So does this improved guarantee look like the profile having all equality?
Yes, it will be all equality.
So even if there were two distinct things and everything else was equal, you can.
Even if there's two. So it's, you don't know which ones are equal, which ones are distinct. So this stronger guarantee simplifies things more. Just say all equal. Yeah. So let me fast forward this. This was the things that we looked at before. So yeah. So this is what we say, that we get inner codes. For every LCL property, we get actually inner codes which satisfy the stronger agreement guarantee. For a general LCL property, you have to say what a bad agreement pattern is. That will correspond to the local profile for that thing. And it will have the same rate as the normal thing for any LCL property that you want. So then what? This implies that for these many coordinates, you will see all equal alphabets. See something like this. Okay. So then you'll see something like this. The inner code guarantee says that you'll see all equal alphabets on these many coordinates. The outer code guarantee then says that you'll see epsilon cubed n coordinates will see not all equal alphabets. Going to be one coordinate where there's a mismatch. So you get your contradiction there. Okay. So I'll conclude with some concluding remarks. The first one I want to say is that there's going to be, in the techniques that we saw, there was a closer match between the probabilistic and explicit constructions, or the techniques rather, because we found a hurdle in the explicit construction step and we used probabilistic techniques to get a stronger inner code that helped us overcome this hurdle. So for this thing is, how can you generalize this result to non-LCL properties, which goes back to the question you asked, what if you have agreements between coordinates? So this we cannot handle, and this is an open question to handle these types of properties. And can we use codes with LCL properties? Now that we know how to construct them explicitly, can we use them for constructions of other pseudorandom objects as well? The third one is, can we reduce the alphabet size blow up even if for specific LCL properties? So that's all I had, and thank you.
Okay, since we're a bit over time, let's take the questions. Levi?